wonderful to have Professor Koya Shimokawa from Ochanomizu University with us. They will talk on applications of band surgery on knots and links. Please, Koya, to you.
Thank you very much, Lorenzo. Thank you very much for having me to this wonderful seminar. I'd like to thank the Science Committee for letting me to give a talk here. So today, I'd like to talk about application of band surgery on knots and links. So my background, I'm a topologist, and my background is knot theory and three-dimensional topology. And my today's talk is application of knot theoretical result to other field like vortices, knots and links, and also DNA topology. So, sorry. So this is contents of my talk. So first, I'd like to give the definition of the band surgery and knots and links. And as application, we'd like to discuss the reconnection of vortex knots and links, and also site-specific recombination of DNA. So actually, I will use the band surgery for a mathematical model of these things. And actually, the situation looks very similar, and those two will be dealt in the same time. I mean that the same mathematical result can be applied to both situations. And after that, I will explain some basic result on band surgery. And for the application, I like to give characterization of pathways of reconnection or recombination, and also characterization of the mechanism. So this is the contents of my talk. Okay, first, I'd like to start with the definition of band surgery and knots and links. So in my talk, the knots and links means the embedding of S1 or disjoint union of S1 into three-dimensional space. Normally, we think the three-dimensional space as a Euclidean R3 or S3. And these are knots and links. And in my talk, there are most of the links appear in my talk is torus knots and links, and especially 2p type knots and links. And this is the definition of the band surgery. I think many of you know it, but I'll define it. So let L denote the link in S3, and I is the interval. And we will consider I times I. So you can consider this as a square. So embedding of the square in a three-dimensional space. And we assume that two sides of the square meets the link. So this is the embedding of the square. So this is the band. The intersection of the band and the link is two sides of the band. So this is an example. So this is a part of the link, and here you see the twisted band. So the square is twisted, half twisted, like this, and this is two sides. So two sides are on the link. And sorry. So here, this is a link, and this side, and this side is on the link, and the other two sides is not on the link. And band surgery is a surgery of the knot or link using this square. So in this case, you will delete two sides here and there, and instead you put the other side, so here and there. So starting from the link as in this picture, by a band surgery using this band, you will have this part. So this is just a local figure, but you have a different knot or link. So this surgery is called band surgery, or sometimes it is called banding. And the band is this one, and we will often use B to denote a band. So this is a band surgery. And band surgery is an example of the rational tangle surgery, and a very simple rational tangle surgery. Okay, so this is a band surgery. And there are two types of the band surgery. One is coherent, and the other is incoherent. So here you will consider the orientation of the knot and link. And L is a link before the band surgery, and LB is a product of the band surgery. And band surgery is coherent if L and LB have the same orientation outside B. So this is an example of the coherent band surgery. So here, from here to there, you do a band surgery, as in this picture. And so this arrow denotes the orientation of the knot. So in this case, the torifol knot is oriented in this direction. And as a result, you have a hop link. And hop link is also oriented. As in this picture, we have this orientation here for this component, and the other, this is the orientation. And if you compare the orientation of the hop link and the torifol, the part of the band surgery, other part of the band surgery, the orientation coincides. In that case, band surgery is coherent band surgery. So this is the definition of the coherent band surgery. And if you cannot, so here you consider the oriented knot and link, and knot and link doesn't have this type of the orientation, then it is called incoherent band surgery. In my talk, I will consider coherent band surgery. The first proposition is that when you consider coherent band surgery, then that changes the number of the components of link. So this is an example. So if you consider this band surgery from 2p torus link to 5-1, this is 2-5 torus knot. Suppose, so if you take a look at this part, then this is a local picture of this. And if you do the band surgery, as in this picture, like here, then you have a 5-1. Then the number of the component is changed by 1. And in general, if you consider coherent band surgery, the number of the components of links change. So this is one proposition. You can prove this by considering the connection outside this local figure, and it is very easy to see. So in my talk, if you do the band surgery, the number of the component always changes. You can also consider a different band surgery, which is called incoherent. Then you can go from knot to knot. Actually, there is some example of the band surgery from yielding the trivial knot from a torifol. If you put the band surgery, band is something like this. When you put the square here, then as a result of the band surgery, you will have a trivial knot. But if you consider the orientation, two orientations from the of the 3-1 and the 1 is different. I mean that you cannot put a good orientation, and that kind of band surgery is called incoherent. So if you have a knot from a knot by band surgery, then the band surgery is incoherent. Okay, and actually there are many results on band surgery from 80s or 90s, and Mario Elden Munoz has a very beautiful result of the characterization of band surgery. And one example is that yielding composite knot or link from a trivial knot or other many result is known. But we also consider some problem on the coherent band surgery from now on. Okay, and we will use band surgery for the following applications. First one is a reconnection of vortex knots and links. So this is a picture taken from a paper by Kleckner and Irvine in Nature Physics. So they shows that so here you see a vortex knot of trefoil, and by a reconnection, the vortex will change into a hop link and a trivial knot and a trivial link. And this change is given by the reconnection. And if you take a look at the local picture, you can use band surgery for a mathematical model of reconnection. And so in their example, trefoil is changed into hop link and trivial knot and the trivial link. And actually, we know that for the antiparallel reconnection can be modeled by coherent band surgeries. But actually there is another type of the reconnection called parallel reconnection. And for this, I think the situation is quite different, and we don't know how to, for not theorist, I don't know how to model it. So I like to learn the situation of the parallel reconnection from now on. And there is another example by Simone and Renzo, the recent paper in Journal of Fluid Mechanics. So this example is quite interesting. Starting from a trivial link. So this is a simulation, and starting from a trivial link, one reconnection will change this into a trivial knot. And the next reconnection happens here, and you have a hop link, and the next reconnection happens here, and you have a trefoil. So a reconnection might go in this direction too. So this is an example of the reconnection and the change of the topology. And another application is for the recombination of the DNA. So here we consider a double-stranded DNA, and we assume that the closed circular double-stranded DNA, and you can see such an example as a plasmid of the DNA or the chromosome of the E. coli. Or when you do the experiment, you often prepare a vector which has this type of shape, closed circular DNA. Then you can consider that as a knot in a three-dimensional space. Actually, there is some picture of the knotted DNA or linked DNA. And by Klaus Ernst and Dewey Sumner's recombination is also modeled using band surgery or, in general, rational tangle surgery. So for this application, the information you will have is the topology of the DNA before the recombination, and that is called substrate. So in this picture, you see a trivial knot. And after that, some recombination changes the topology of the DNA, and as a result, you will have this topology. So here, actually the number of the component of the DNA is changed, and you will have 2,4 porous link. And their method is using this information, they will characterize what is happening inside this three ball. Recombination of the DNA is a local change of the DNA, and actually cut the DNA and reconnect in a different way. But as you can see in this picture, what is happening cannot seen from my experiment. So using this information of the topology, they characterize the mechanism of the recombination. And so they use, in general, tangle surgery or sometimes band surgery to do research on this situation. And this is a mathematical model of the recombination. So this is a tangle which models the complex of the enzyme, which can be seen here. So this is a three-dimensional ball, and in this ball, the recombination happens, and the recombination is modeled as like this. So this part is cut and reconnect in this way, and you have this picture. This is a mathematical model of the recombination. And inside the ball, some part is not changed, and that is expressed the tangle O. So here, you will see you have some structure which is explained in a two-string tangle. And so this is a mathematical model of the recombination. And if you know tangles, so this is a mathematical explanation. So this part is this part is expressed by a tangle O, and this part is expressed by tangle P. And the whole piece of the tangle is expressed by a tangle sum of O and P. And this n is a numerator, so this means that this part is connected to this, and this part is connected to this. So NOP is some knot or link, which is a substrate, and the P part is changed into R part. So as a result, you have this. So tangle sum and O and R, and the numerator will give you the product knot or link. And the information of the substrate and product, we like to characterize what is happening inside the ball. So this is one example of the idea by Klaus Ernst and Dewey Sumners. So here you can also use band surgery for a model recombination of the DNA. Okay, so far I explained the definition of the band surgery and examples and example of the application. So here we discuss reconnection of the vortex knot and links, and also recombination of the DNA. So 18. So from now on, I will go further to property of band surgery of not theoretical part, and after that I go application. Are there any questions so far from the audience?
Koya, can you clarify band surgery? So far, you didn't talk about surfaces, right? So it's not in the picture, not yet. But you have in mind of Zyphus surfaces connected to this?
Yes, that's right.
Okay. Thank you.
Are there any questions?
Koya.
Yes.
Koya, can you just go to your last slide you showed?
Yes. This one?
That one. So this one is a jump from link to knot. So that is a coherent.
Yes.
One.
Yes.
If or incoherent one, it could be from knot to knot or link to link.
Yes, that's right. So
okay.
Incoherent one. So when you have a knot that is incoherent. Yes.
Okay. So the reconnection you show here, it is a anti-parallel reconnection.
Yes, that's right.
Okay. All
Ah,
right. Just
I see. I see. So when you consider a parallel reconnection, you have a not. Maybe. So actually, that's what I don't know. But here we consider not to link or link to not. Thank you very much for your question.
no worries. Thank you so much. Yeah.
Okay. If there is no question, I will go further.
Hi, Koya. I have a question.
Yes.
I think if we are considering the oriented nodes, I don't understand how could incoherent reconnection happen for the nodes who have the orientation. What do you think?
So when you can put orientation in this way, then it's coherent, and incoherent means correspond the case where can you see my pointer? So if you put a very small square here, then the band surgery, you have this and this knot, like this, and that will be a trivial knot. And when you consider such an example, here, whatever the orientation you will put here, it is not consistent with this old orientation. So the new link, new knot goes like this. So this part follows the orientation, but you have to go this way. And there, the orientation doesn't match. And whenever you have a knot from a knot to knot band surgery, then this situation happens, and then it is called incoherent band surgery. Do this answer your question, or maybe I explained the different things?
I'm drawing a picture to try to understand.
So when you consider knot to knot band surgery, there is no way to put the good orientation which matches this picture. So here, suppose this part is connected to this and this part connected to this. Then this part also connected to this and this part also connected to this. Then both cases you have a good orientation which is only given by this picture. But incoherent band surgery, you cannot do this, and so that is the point. Maybe I will explain this
Sure.
part later. Sorry about that.
Yeah.
Thank you very much for the question. And okay, next I will explain some of the result on band surgery, and then after that I will explain my result as application to DNA and reconnection. So this is the mathematical part. First, we will consider a Seifert surface, which Renzo mentioned. So starting from an oriented link. So this here you fix orientation of the link. So in this picture, you see oriented trefoil. And the Seifert surface for this link is a compact oriented surface with boundary, and also has a orientation which agree with the orientation of L. So this left right one is the Zyphus surface of this link L. So this is orientable surface, and which agree with the orientation of the L. And this is called the Zyphus surface. And if you consider a defect line of the vector field, and sometimes you can consider isophase surface. And isophase surface can be considered as an example of the Zyphus surface. And for the research on Zyphus band surgery, sometimes you will use Zyphus surface for defining some invariant called a signature. And also, I have one result where the characterizing band surgery using minimal genus Zyphus surface. So I will explain this part. And from the Zyphus surface of L, you can define a signature of the link. And I'd like to explain briefly the definition of the signature. And you can see the definition of the signature in a textbook of the knot theory. First, you take a one-dimensional cohomology group of the Zyphus surface and the basis of the one-dimensional homology group. So here you have two generators. And from this information, you make a Zyphus matrix. So when you have two, the matrix is defined by a linking number of two generators, but one generator is moved so that they will make a link and consider the linking number of the two generators. In this example, A and B, and if you move A above and consider the linking number of A, and that is -1, and that is correspond to this part. And the linking number of A and B plus is 0, and you have 0, and the linking number of B and A plus is 1 here, and also the linking number of B and B plus is -1, and you have this M. And this is called a Zyphus matrix. And you take transpose of M and consider the sum of M and transpose M, and you have a symmetric matrix. And the signature of the matrix is called the signature of the link L. And actually, this signature is an invariant of L. And in this example, from the Zyphus matrix of the torrefier, you have this Zyphus matrix, and M plus transpose M is this one. And if you calculate the eigenvalue, you see the signature of 3, 1 is -2. And actually, you can calculate the signature of links. And well-known theorem is that the signature is a link invariant. And you can use this invariant for the study of band surgery. And this is the result by Murasugi. If you consider a coherent band surgery yielding LB from L, then the signature doesn't change much. And the absolute value of the difference of the signature is at most 1. So you can use this theorem for showing the non-existence of the band surgery, or you can also use the number of the band surgery or reconnection or recombination you need to have the product. For example, if you start from 2,6 torus link, and so here you see the parallel orientation, then the signature is -5. And if you like to consider a sequence of band surgery yielding the trivial knot, then from that, using the signature, you can count the number of the minimal steps you need. The signature of the trivial knot is 0, and the signature of this link is -5, and the coherent band surgery only changes signature at most 1, so you need at least 1, 2, 3, 4, 5 steps to have this. So this is one application of the signature of the band surgery. And the next one, and also the signature mathematical result is very old, and also recently, or 13 years ago, Karnov shows that you can also use Jones polynomial or Q polynomial to determine, to show actually this example is, these theorems are used to show the non-existence of the band surgery, but Jones polynomial and Q polynomial also gives the information of the existence of the coherent band surgery. So this is a ratio of the special value of the Jones polynomial. And this is a ratio of the special value of the Q polynomial. Sometimes we will use this to show the non-existence of the band surgery. And also, alpha invariant can be used for the non-existence of the band surgery. Next one is my result, and also the same result is shown by Sharman Thompson and also dual Miyazaki Motegi. Sharman Thompson, I think 1994, and my result is 2000, and DMM is 2006. So this shows that if coherent band surgery reduces the complexity of the link, then you can show that the band can be isotoped on some minimal genus surface. That is the meaning of the theorem. So here, Chi-L is a maximum value. So this is the Euler characteristic of the link L. That is a maximum of the Euler characteristic of the Seifert surface of L. And this means that the Euler characteristic goes up, then you can characterize the Seifert surface. And this means that the Seifert surface will be will have the reduced complexity. So the Seifert surface will become simpler, then you can have some characterization. So that is the meaning of the theorem. And the theorem shows that the band can be isotoped on the Seifert surface. And the Seifert surface is a special Seifert surface called a taut Seifert surface. And the taut Seifert surface is not easy to define, and this means this is almost like a minimal genus Seifert surface. There is a little difference, but normally it means a minimal genus Seifert surface. So sometimes I use this to characterize where the band is. And if you apply this for the antiparallel reconnection, and suppose the reconnection makes the nodal links simpler, then you can show that the antiparallel reconnection happens on a isophase surface. So that is the meaning of this theorem. So this is one example. Suppose you have a trivial knot from a torus link with a antiparallel orientation. So this example is different from the old one. So in this case, the minimal genus Seifert surface or taut Seifert surface is annulus between these two components. And that theorem shows that if you have a trivial knot, then that band can be put on annulus. And as a result, you can show that the band is isotopic to this band. So as an application of that theorem, you can sometimes, if you are lucky and the surface is very simple, sometimes you have a characterization of the band surgery. And in this case, torus link with antiparallel orientation, you can succeed to have a characterization of the band up to isotopy. Okay. So this is a mathematical result which I will use today for application. And I'd like to discuss some application, and today I mainly use that example of the DNA, but actually the situation or topological change is same as vortex knots and links and the reconnection. Okay, so here we will consider unlinking DNA by site-specific recombination. Normally, DNA is unlinked topoisomerase in a cell, but we will consider unlinking by site-specific recombination. So for the experiment, first they prepare DNA with this topology, and you can put orientation of the DNA, and in this case, so you have a 2-2N torus link type DNA, and the orientation is parallel, as in this picture. And the sequence of the recombination, you will have unlink as a result. That is the experiment of the DNA recombination. And we like to characterize the pathway of the recombination. We like to show how this DNA link is unlinked by a sequence of recombination. And so from our experiment, a DNA experiment, this is what you get. So you see some gel result. And from this gel, you see what is happening. And so how you read is as follows. So from the first, you see various of links and two hop link or 2-4 torus link or others. And after the recombination, this complex knot will be reduced, and as a result, you have trivial link. And we like to characterize these recombinations. But if you like to make a mathematical model, so it's vague, and you need to make a good assumption. And from this experiment, we make the following assumption. It seems that the complexity of the DNA goes down, and the complexity here is means the crossing number of the link. And we will use this as an assumption. The recombination reduces the crossing number, and as a result, you will have a trivial link. And from this assumption, we like to characterize the pathway. And this is one pathway, starting from 2-6 types link, which has a parallel orientation, and as a result, you have a trivial link. And actually, you need several recombination, or when you consider vortex link, you will consider reconnection to have a trivial link. And we like to characterize the pathway. I mean that what is intermediate product during this unlinking event. And we will use a coherent band surgery for a model of the recombination or reconnection. And for example, this is one example of the unlinking pathway. Starting from 6 to 6 by a coherent band surgery, you will have 5-1, and another band surgery here, you have 2-4 torus link, and next one you have a trefoil, and so on. And 1, 2, 3, 4, 5, 6 band surgery or recombination or reconnection, you have a trivial link. So this is one example. And actually, this shows that recombination can be considered as a band surgery. When you consider a trivial, DNA not a link, you can use the site to give the orientation. And site-specific recombination, there are two sites, and the recombination happens here. You cut this site here and here, and reconnect in the different this way. And as a result, you have the same site. So this is a recombination, and the site has some orientation. And using orientation of the site, you can give the orientation of the whole structure, not a link. And using this orientation, you can show that the recombination is can be modeled as coherent band surgery rather than incoherent. So here we will use coherent band surgery as a model of the recombination. And when you consider vortex Norton links, and you also consider antiparallel reconnection, you can use the orientation of the vortex, and you can use coherent band surgery as a as a model of the antiparallel reconnection. Okay, so this is the model, and first we consider the characterization of pathways. And the problem of this type, you will consider the pathway and also the characterization of the place of the reconnection or the mechanism of the reconnection or the recombination. So there are two types of the problem we will consider, and we will discuss first characterization of the pathway, and the next characterization of the mechanism or the place of the reconnection. And so here we will consider the following assumption, which corresponds to the DNA recombination experiment. Also, example of the reconnection due to Klecker and Irvine. The first assumption is that reconnection is a coherent band surgery and oriented knots and links. And here the link is one or two component. And when you consider reconnection of the vortices, sometimes you have 3 components or 4 components. And but here we only consider 1 or 2 components. And next is following assumption that the reconnection or recombination reduces the topological complexity. And here we use crossing number as a topological complexity. So that is our assumption. And actually, without these assumptions, there are many other examples, and actually you can find infinitely many different results. So we need some assumption to have some result. So this is our assumption in today's talk. So the first one is the characterization of the pathway. So starting from a parallel 2,6 torus link, and we assume that the product has a less crossing number. So starting from 6 crossing, suppose you have 5 or less crossing, and what do you have? So that is a question, and the result is the following. If you start from a 6 link, 6 torus link with a parallel orientation, so this is the only result. So you have 2,5 torus knot. So that is one. You have the unique product. So that is one theorem. And if you consider antiparallel orientation, you have a different result. But if you consider parallel orientation, this is a unique result. And the next step, starting from 2,5, 10, and you assume that the link with at most 4 crossing. Then you can also show that the result is unique. And actually, you can continue, and you can do it in general, starting from 2 to n. So you have 2n crossing, and if you assume the crossing number go down, then you have a unique result. And starting from a torus knot of this type, and the corresponding number goes down, you also have the same. Also have the unique product. So this is the result we get starting from 2n torus link with spiral orientation. And if you assume the crossing number goes down every time, then you have the unique pathway. So that is the result, and this can be used for the recombination, the result application of the DNA recombination and the reconnection with with a given assumption. And so this is a proof. So here you use the relation between the absolute value of the signature and the crossing. So we show that the absolute value of the signature is bounded above by the crossing number -1. And if the equality holds, then we can also characterize the knot or link. So that is the proposition. And using this proposition, actually you can prove the theorem. And this is how you get. Starting from this, then you can calculate the signature. Absolute value of signature is 5. And by the theorem of Munasugi, the coherent band surgery changes the signature by 1. And we assume that the crossing number goes down. First, you assume the crossing number goes down. Then, by this proposition, the signature is bounded by 4. And the next, using the Murasugi's theorem, the signature only changes by 1. Then you can determine the signature of the product. And if the crossing number is less than or equal to 4, and if you have this signature, by this proposition you can characterize the knot. So that is proof of the theorem. And the proof of the proposition is as follows. Actually, that can be done by using the Seifert surface and by using the Euler characteristic of the Seifert surface and what is this? The number of the Seifert circle and the crossing number. So Seifert circle is when you have a diagram, by smoothing you will have number of the circles, and that is called the Seifert circle. And the number of the Seifert circles can be is denoted by SD. And using those numbers, actually you can prove the proposition. But I will skip the proof. If you are interested, please take a look at the paper. Okay, and if you relax the assumption, and I mean that the crossing number can stay same or goes down, then you have a little more pathway. And if you start from 6 crossing torus link, then you can show that there are 9 shortest pathway. So here we assume that you will have a trivial link in the shortest pathway. That means that by 6 steps, 6 reconnection or recombination, you will have a trivial link. So that is one assumption. And the crossing number stays the same or goes down. That is second assumption. So if you assume both, then this is the only pathway. And if you allow more steps, maybe 8 steps, so actually even number of steps. So 8 steps or 10 steps, you can find a little more interesting pathway. But if you only consider shortest, then you can show there are 9 pathways. Okay, and I will skip this. And for the characterization of the mechanism, we will use the Seifert surface of this. these links. And for the mechanism, we like to characterize the I2P class of the band surgery, or where the reconnection or recombination happens. Well, first example is a 12-fold node to hop link. Suppose a coherent band surgery yields hop link from a 12-fold node. Then we can show that the band surgery is unique up to I2P, and the band surgery actually happens in this way. So that is the result. So the band surgery is unique. And here, we will use the Duffield surface of the trefoil. And actually, So I show that if the complexity goes down, then you can show that the band surgery can be put on the Duffield surface. And for this trefoil knot case, the Duffield surface is so as in this picture. This is the example of the Duffield surface, and our result shows that you can isotope the band on this surface. And in this case, you can show that the band can be put here, or here, or here. So you have the characterization. And in general, we show the following. Starting from a genus 1 two-bridge knot, which can be written as this. And suppose you have a torus link as a product by a coherent band surgery. Then the band is isotopic to one of these four. So that is the result in paper 2012. And as a special case, we have a characterization of the band surgery from a trefoil knot to hop link. Okay, so we know the mechanism of this reconnection or recombination. And the next one is an example of the hop link to trivial knot. And we can also show that the band surgery is isotopic to this one. So band can be put here. So this can be shown by a paper with Hirasawa, and also Thompson also considered this type of banding in 1989, and showed that band surgery is isotopic to this one. So band surgery is unique up to isotopy. And from a trivial knot to trivial link, Sharman shows that 1985 that the band is unique up to isotopy, and the band happens this, as in this picture. Okay, so from this to this corresponds to an example of the Simone and Renzo's simulation. So if you like to have oriented trivial knot from trivial link, then you have to do this. Okay, so we know this mechanism, and for these examples, we also consider characterization of band surgery from this type of torus knot link to this type of torus knot link in 2016. So we show that it's a same situation as the case of the trefoil knot hop link. And to prove this theorem, we characterize the band surgery from a fibered link to fibered link. So the paper appeared in JLMS 2016. Here we consider a fibered link. That is the link whose complement has a fibered structure. That is here we consider L is a fiber link, And also, after band surgery, you have a 5-word link. And we assume that coherent band surgery surgery reduces the complexity of the xiphoid surface. So that means that the link will be a little bit makes simpler. Then we can characterize the band surgery. So we only consider this case, but other case is also considered by Tsuyoshi Kobayashi. So we this case is left, and we characterize this case. And if you have a band surgery from 5-word link to 5-word link, then the band surgery can be written as a generalized hop banding of a xiphoid surface. So this is a picture of the generalized hop banding. This is drawn by Ken Baker. And this is seems like looks like a hop banding, but a little bit generalized. So using this theorem, we characterize the band surgery from torus link, 2p type torus link to 2p type torus link, or 2p type torus link to connected sum of the 2p type torus not link. And for example, if you have this is one example starting from torus link 2p, and suppose you have LB by coherent band surgery, and assume that all the characteristic goes up, then we have a characterization that the link is this one, which appeared in the previous sheet, and also connected sum of this. And actually, the band is unique up to isotopy for this case. So using this, we have a characterization of the band surgery. And I'd like to show the characterization of the band surgery of these examples. So starting from 2 to 6 torus link, you have this torus knot or connect sum of this. And from using our theorem, we can characterize band is unique up to isotopy. So if you have 5-1, then the band is isotopic to this one. And if you have torus connected sum of 2 trefoil knot, then the band is isotopic to this one, actually up to symmetry. And using this theorem, you can characterize these red arrows. And for the black arrows, we know some example of the band surgery, but we don't have characterization of the band surgery. So if you are interested in, please characterize these band surgeries. And from the rest of my time, I'd like to show you some pictures. So here we have the uniqueness of the band surgery. And that corresponds to this part. And here, we know that this is just an example of the band surgery. From this one to this one, we know this is one example, but we don't have a characterization. And this one is also an example, and we don't know the characterization. And for by application of the theorem, we can also characterize the band surgery from the connected sum of the torus knot link to this one. And using this, we have a characterization of the band surgery from here to there. Okay, so these are the examples, and I think it's almost time, and I skip this. And so the main collaborator of this type of work is Mariel Vasquez and also Kai Chada. And actually there are several other collaborators, but these two are main collaborators. And this is findings of my research. And thank you very much. That's what I want to say. Thank you.
Hey, thank you very much. Thank you very much, Koya, for this wonderful talk. Are there any questions? Koya, maybe I have one for you.
Yes.
You take the case of the 2-6 knot, and then you show that it goes either to the connected sum of the trefoils or the the 2-6 link, and it goes either to the connected sum of the trefoils or the knot 2-5.
Yes.
In terms, is any way to identify by using information you have to identify a preferred choice for a lesser complex Cipher surface attached, say, to the 2-5 knot rather than the connected sum of the trefoils?
I see. So in this case, Cipher surface is so this type. So 2-6 torus link, you have this type of Cipher surface. So you have 6 crossing here. It's the picture is different, but you imagine that there are 6 crossing. And our theorem show that the band can be isotoped on this Cipher surface. And I think it depends on the shape of the Cipher surface in your situation. And normally you will have a symmetric, and I think you have a minimal surface as a Cipher surface. And I think the band surgery, which will give you the 5 crossing torus knot, happens. The band surgery is near the crossing, so here or there. And if you for the other case, the band has to connect these two. Maybe it is good to have a symmetric picture. So in this picture. So here, in this case, you have 2 disks up here and down there, and the 2 disks is connected by a vertical half twist band. I think that is the surface of this surface. And the band or reconnection happens near the vertical twist, then you have a 5-1. And if you have band as in this picture, you have the connected sum. So I think normally this band or this reconnection is you need a long band to do this reconnection. So it seems this is the rare case. And I think the reconnection happens very near place, like at a crossing, then this happens. So
maybe a minimal area, a least area consideration may play a role in this.
Yes, and I think you can discuss the length of the core of the band surgery, which gives the product. And most of the case, the short one will give you 5-1, I think.
Okay, thank you. I'm sorry, but just following up, is any information we can take from the signature in terms of Cipher surfaces, or maybe it has a role?
Yes. So signature is given by this Seifert matrix, and the size of this Seifert matrix depends on the number of the bases of the Seifert surface. So you take a minimal genus Seifert surface, and that will give you the upper bound of the absolute value of the signature. So, so that can be said. And do you want some more information from the Seifert surface?
Well, for the moment, just thank you for the moment. I wonder if anybody else has questions or comments.
Koya.
Yes.
Koya? Xin
Yes.
speaking. I have understanding that you are just using the signature sigma. Maybe the Euler number chi as well as a either to measure the complexity of the and the length. Is my understanding good or not?
So for the characterization of the bound surgery, we use so for the characterization of the bound surgery, we use the Euler characteristic to show the uniqueness of the bound surgery. So in our example, the closing when the closing number goes down, and so most of the case, the Euler characteristic also goes up. So we can use this theorem. So I think in a situation we can this satisfy this assumption is satisfied. So we can use this theorem to show the bound surgery is unique. But in general, we don't know this. So if you like to use this, we also need this information. So what I use is that in our case, this is satisfied, so we use this theorem to show the uniqueness of the bound surgery.
Okay, so that means I remember you just give some assumptions on page 29 and page 43. Some assumptions. So that means maybe in future, I'm just curious, maybe in future you can give us some proof of those assumptions by using sigma and chi or something. Yeah. I think that will be interesting.
Which part? Here.
No. What I mean is maybe in future you can give us some proof of your assumptions by using sigma or chi or other things, other topological numbers or invariants or something. Yeah.
Just a moment. This part?
You just to give us a proof.
This one?
So that means the proof for your assumption?
No. So this, no. So assumption is a assumption, and we don't give a proof.
Okay. What I mean is, maybe in future you can just give us some more information, further information about a kind of proof or something. Yeah. Thank you.
So for the assumption of the closing number goes down. Where is it? So we often give that the closing number goes down or same as assumption. The reason why is that if you allow that the closing number goes up, you can find infinitely many different ways to go to trivial link in 6 steps. Even if you assume that there are only 6 steps, if you remove the assumption of the closing number, you can find infinitely many different ways. So, so we need some assumption to give some characterization. So that's why we often put the closing number. So closing number goes down or stay the same. And actually, when you consider DNA, so this assumption is good with the experiment. So we often put that.
Yeah. Thank you so much. Thank you.
Thank you very much.
Other questions or comments? Okay, if not, thank you very much. Thank you, Koya, again, and
thank you very
you
much.
all for listening and watching. Thank you.